Whether you are writing search engine algorithms, calculating quantum energy states, or predicting how a skyscraper will vibrate during an earthquake, the math behind all these systems relies on understanding linear operators. But there's a practical problem. An operator transforms an entire vector space. How do we fully understand its behavior without testing every single vector one by one? We look for the invariant directions. Notice how, as this grid transforms, certain vectors are only scaled, never knocked off their original line. We call these special vectors eigenvectors, and the scaling factors applied to them are their eigenvalues. Let's track down these invariant properties mathematically using a concrete 2x2 matrix from the text, where the top row is 5, 4, and the bottom row is 1, 2. Theorem 7.12 tells us exactly how to find the eigenvalues. They are the roots of the matrix's characteristic polynomial. We subtract a lambda times the identity matrix from a matrix A and set the determinant of that result to 0. For our specific matrix, the algebra gives us lambda squared minus 7 lambda plus 6 equals 0. Factoring that polynomial yields exactly two roots. Lambda 1 equals 6 and lambda 2 equals 1. For a finite dimensional matrix like this specific set of scaling factors, 6 and 1, is all we need. This collection of eigenvalues is what we call the spectrum of the operator. We have our spectrum, but there is an immediate friction point. The numbers inside a matrix change depending on the basis, the coordinate system, we choose to represent our vector space. If we map the exact same physical transformation using a skewed coordinate system instead of a standard grid, the matrix looks completely different. Does this mean our spectrum changes too? Theorem 7.1-3 gives us the answer. The spectrum is independent of the basis representation. It is an intrinsic property of the abstract operator itself. We can relate any two matrix representations of the same operator using a similarity transformation. The matrix for the skewed grid, T tilde E, is equal to C inverse times the standard matrix TE times C, where C is our change of basis matrix. To prove the spectrum survives this coordinate change, we construct the characteristic polynomial for the new skewed basis. We start with the determinant of T tilde E minus lambda I, and then substitute our similarity transformation into the equation. Now it's your turn. Pause the video and see if you can simplify this expression. Try factoring out the C matrices on both sides of the lambda I term, and then apply the rule that the determinant of a product is the product of the determinants. Let's look at the result. When we split the determinants, we get the determinant of C inverse multiplied by the determinant of C. Since these are inverses, they cancel each other out to exactly 1. The outer matrices vanish, and the equation collapses right back into the determinant of TE minus lambda I. Because similarity transformations preserve determinants, the roots remain identical. The spectrum is a permanent, unchanging property of the operator. We know the spectrum is permanent, but we still need to guarantee that it actually exists. The existence theorem, 7.14, states that a linear operator on a finite dimensional complex normed space is guaranteed to have at least one eigenvalue. The word complex in that theorem is strictly necessary. To see why, look at this standard two-dimensional Cartesian plane and consider an operator that rotates the entire space exactly 90 degrees. Every single vector in the space is pulled off its original span. Because no real vector maintains its original direction after a 90-degree rotation, this operator has absolutely no real scaling factors. Its characteristic polynomial is lambda squared plus 1 equals 0. If we restrict ourselves strictly to real numbers, this equation has no solution, meaning our spectrum would be completely empty. The fundamental theorem of algebra guarantees that every polynomial has roots, but only if we allow complex numbers into our calculations. By working within complex normed spaces, we ensure that the characteristic polynomial always resolves. This mathematical environment guarantees that an operator spectrum is never empty, giving us a reliable foundation to analyze any transformation. As we prepare to move beyond finite matrices and into infinite dimensional spaces, we need to upgrade our vocabulary. We define the shifted operator, T lambda, as T minus lambda I. If we can invert that operator, we call the inverse the resolvent operator, denoted as R lambda. The resolvent maps the complex plane into two territories, the resolvent set, ρ, with a bounded, dense inverse. The remaining spectrum divides into three regions: the point spectrum, lacking any inverse, the unbounded continuous spectrum, and the residual spectrum, which leaves gaps in our space. As summarized on this cheat sheet, finite dimensional operators only possess a point spectrum. The continuous and residual regions are completely empty. But as we move into Chapter 7, mapping these regions provides the structural framework for navigating the unbounded behaviors of infinite dimensional spaces.